Today's lesson will be on writing polynomials, their end behavior, and symmetry. So we just finished learning how to solve polynomials by finding the zeros or the roots or the answers, the solutions. Those are all words that mean the same thing. Now this time we're going to be given the answers and go in reverse to write our polynomial. So just to kind of recap, we want to go ahead and review how we solved a polynomial. So we've got x squared plus 3x plus 2. Now this is something that I would use x factor on. So I'm looking for numbers that multiply to make 2, add to make 3, and those numbers would be 1 and 2. So when I factor this, this is x plus 1 times x plus 2. So this would be the factored form. And then we would set each factor equal to 0 and solve for x. And these would be my zeros, roots, solutions. Those are all the same thing. Okay, so what we're going to do is we are going to start from the bottom, start from the last thing that we did, and work backwards. So we want to write a polynomial with least degree. And really all this means, this least degree, means the smallest possible exponent. That has rational coefficients, so that basically means no radicals, no imaginary numbers, something that can be written as a fraction. A leading coefficient of 1, and 0 and 5 are the zeros, or the roots. Okay, so here's what I know. I know that x equals 0. I know that x equals 5. And so I'm going to write these as factors. So first I want to write as factors. So with a factor, we want to get it set equal to 0. So for this one, it's already set equal to 0. So I'm going to write x. And then to get x equals 5 equal to 0, I'm going to subtract 5 from both sides. So x minus 5. So this would be my factored form. And then the last thing I'm going to do is go ahead and distribute that. So that becomes x squared minus 5x. So that would be my polynomial. So least degree, smallest possible exponents. The rational coefficients, remember no I, no radical. Leading coefficient of 1 means that there's no greatest common factor. So actually, let me write that real quick. So all right, so let's try another one. We've got a polynomial with least degree that has rational coefficients, a leading coefficient of 1. That's pretty much always going to be the same. What's important is this right here. 3, 2, and negative 2 are my zeros. So once again, I'm going to write, I've got x equals 3, x equals 2, and x equals negative 2. I want to write those as factors. So this is going to be x minus 3, because remember we would want that to be equal to 0. This is going to be x minus 2, and this is x plus 2. And I just realized I never wrote the second step up here. The second step is to multiply. So I'm going to multiply these together. Doesn't matter which one you start with. I do see that I've got minus 2 and plus 2 here, so I'm going to start with that one. So I'm going to do x minus 3. And I know that these are factors of a difference of squares. So this is going to be x squared minus 4. And then I can distribute, I can use FOIL, I can use the box method, but it's going to end up giving me x cubed minus 3x squared minus 4x plus 12. All right, let's do one more just to kind of make sure we understand. Again, generally this is going to be the most important part because the rest of it is all the same. So x equals 0, or sorry, x equals 3 and x equals 5. I want to write those as factors, x plus 3 because that would equal 0, and x plus, sorry, said that wrong. X minus 3 would equal 0, and x minus 5. And then the last thing I'm going to do is multiply those together. So that's going to give me x squared minus 8x plus 15. So there are some theorems that I want you guys to know. We've talked a little bit about these before. The first one is the complex conjugate theorem. So when we talk about complex numbers, we're talking about imaginary. So we're dealing with our i's. So if I have something in the form a plus bi, if that is an answer, then its conjugate also has to be an answer. And remember, the conjugate, we're just changing the sign in front of the imaginary term. So this right here is the conjugate, the whole thing. So for example, if I is a root, if I is a solution, then so is negative I, because I'm changing the sign in front, and this was originally a plus. Then if 2 minus 4i is a root, I'm changing this sign right here, so then so is 2 plus 4i. So the same thing is true with radicals. So this is called the irrational. So this is when we're dealing with radicals. So if a plus radical b is a root, then the conjugate, remember we're changing the sign, but this time instead of changing it in front of the imaginary number, we're going to change it in front of the radical. So then a minus radical b must also be a root. So some examples, if the square root of 2 is a root, then so is negative square root of 2. If negative 5 plus 7 is a root, remember we're changing only the sign in front of the radical. So we're going to keep that negative 5, we're going to keep that radical 7, and we're going to change that plus to a minus. So for these theorems, it's usually easier to multiply either the complex factors or the irrational factors, depending on what your problem has. It's usually easiest to do that first. So that would be my recommendation. So let's try these out. So we want to write a polynomial function of least degree with rational coefficients, a leading coefficient of 1 and 2, and radical 6 as zeros. So I'm going to write my zeros. I'm going to zoom in a little bit. So I've got x equals 2. I have x equals square root of 6. But because of my irrational root theorem, I also know that x equals the negative square root of 6. So I'm going to write my factors. So this is x minus 2. This one is x minus radical 6. This one is x plus radical 6. So I'm going to start multiplying all those together. I am going to do these together first. So when I multiply those together, let's see, let's come over here. I've still got that x minus 2 to deal with, but that x minus square root of 6 plus, or times x plus square root of 6 is going to give me x squared minus 6. And now when I multiply those together, I'm going to get x cubed minus 2x squared minus 6x plus 12. So it's really just remembering to write the opposites as answers as well. All right, let's do that one more time. So polynomial, least degree, rational coefficients, leading coefficient of 1, and then here's what we really care about. 0, 3, and negative 4i are my zeros. So I'm going to write x equals 0, x equals 3, x equals negative 4i, and then this is where our complex conjugate theorem comes into play. That means x equals positive 4i is also an answer. So when I write these as factors, this is just x. This is x minus 3. I have x plus 4i and x minus 4i. So I'm going to kind of do this in two parts. I'm going to do this part here first and this part here second. So x times x minus 3 is going to give me x squared minus 3x. So I'm going to leave that for a second. When I do x plus 4i times x minus 4i, that's going to give me x squared minus 16i squared. Now, I don't know if you remember, this was a while back, but we learned that I squared equals negative 1. So I am going to replace this with negative 1. So that's x squared minus 3x times x squared, and then negative 16 times negative 1 gives me positive 16, so plus 16. And now I'm going to multiply those together. Now again, you can use the box method, you can use FOIL, you can use distributive property, totally up to you what you choose to do. It should give you an answer of x to the 4th minus 3x to the 3rd plus 16x squared minus 48x. All right, so now we're going to move to something else. We're going to move to end behavior. I like to call this the robot dance. So with end behavior, we've talked about this with quadratics in Algebra 1, and we talked about this a little bit with exponentials in Algebra 1 as well. And then obviously with linear functions, we've talked about that as well. We're going to do the same thing, and we are going to be able to figure out which way the end behavior is moving based on the degree and the leading coefficient. Okay, so if the degree is even, so 0, 2, 4, 6, 8, etc., and the leading coefficient is positive, we're going to call this E plus, so even and positive. So I'm going to draw this little man. Now, don't make fun of me. I am not an artist, but I'm just going to draw this little man right here. I'm going to draw him in each box. So we're ready to just draw his arms when the time comes. So I'm going to, when we have an even degree and the leading coefficient is positive, his arms are gonna go whoop, like that. So to kind of write that in words, because whoop is not going to help you at all on your test. So if we're talking about the left end behavior and the right end behavior, the left, if I were to start here in the middle and move left, I'm moving upwards. So I'm going to write up. If I were to do the same thing to the right, start in the middle and move right, I'm still also moving upwards, so up and up. All right, the next one, degree is even, so E for even, and the leading coefficient is negative, so this is E minus. My arms are going to go whoop, like that. Kind of looks like he's doing the wave with his arms. So my directions, as I move to the left, I'm moving down. And as I move to the right, I'm also moving down. So one thing that I'm noticing is that my even degree, they both move in the same direction. All right, let's deal with some odds. We're going to call this O, and then leading coefficient is positive, so O positive. Let's look at my little man. His arms are going to do this little like that. So if I'm looking, if I started in the middle and moved to the left, his arm is moving down. If I start in the middle and move to the right, his arm moves up. And then my last one, if the degree is odd and the leading coefficient is negative, this is O negative. I'm going to come over here and draw his arms like these two. This is really going to date me, but these two really remind me of Saturday Night Live. Saturday Night Fever, not Saturday Night Live. Saturday Night Fever, where John Travolta's like, whoa, and he like throws his arms in opposite directions. Anyways, okay, that's probably way, way older than you're used to, but. So as I move to the left, his arm is going up. As I move to the right, his arm is going down. So one thing I'm seeing here is that when my degree is odd, they move in opposite directions. Another pattern that I noticed is that for the right side, whatever the leading coefficient is, determines how it moves. So if my leading coefficient was positive, the right side moved up. Leading coefficient was negative. The right side moved down. So we are looking at the degree, and then the leading coefficient tells me how the right side moves. So let's look at each polynomial, and we're going to figure out the end behavior. So the first thing I want to do is I want to figure out, okay, is this positive or negative? So I'm looking at the leading coefficient. The leading coefficient here is -2, so this is a negative function. Then I want to look at the degree and see is it even or odd. My degree is the highest exponent. In this case, it's 4. 4 is even, so this is E minus. So I can either go back to my chart and try to figure that out, or I can remember that E means the same. They move in the same direction. And the minus tells me that my right side is going down. So then, since they're the same, the left side is also going to be going down. Now, this is probably going to be some familiar notation to you guys. On the left, we say as x moves towards negative infinity, which means as x moves to the left, f of x, or as we usually say, y, moves to negative infinity, or in this case, down. For this one, the same will be true of the right, only this time as x goes to positive infinity, f of x goes to negative infinity. They're going in the same direction and they're both moving down. All right, number 2, my degree here, my highest exponent is 3, so that is odd. So I know that my arms, my robot arms or my end behavior are going to be going in opposite directions. And then my leading coefficient is just 1, so it is positive. So they're both going to be moving, or sorry, my right side is going to be moving up. So for the left and the right. So the left is always x to negative infinity. The right is always x to positive infinity. Because think about on a number line. You're going to move left as you get more negative and right as you get more positive. So we said that this positive tells me which way the right arm moves. So the right arm is going to go to positive infinity. But since the degree is odd, they are going to move in opposite directions, which means that the other arm will move towards negative infinity. All right, number 3, we're looking at an odd negative. So they're going to be opposite directions. So x to negative infinity and x to positive infinity. Now remember, the plus or the minus at the end tells me which way the right is moving. So the right is going to be moving down towards negative infinity. Since it's odd, they are opposite. So the left will be going to positive infinity. You could also just write infinity. You don't have to write the positive sign. And the last one, we're looking for the highest exponent, in this case 4, so that is even. And then the leading coefficient goes in front of it. It is positive, so this is e positive. So the left, as x goes to negative infinity, f of x goes. So even means that they are going in the same direction. Positive means they are moving up towards positive infinity. So the same thing will be true on the right as it moves towards towards positive infinity. F of x moves towards positive infinity. All right, one last thing before we finish it out today. So when we're talking about symmetry, remember symmetry means that you have the same thing on both sides if you folded it in half. So symmetry is all about the exponents. So we do need to remember a lot of times we don't write exponents for when the exponent is 1 or 0. But we do need to remember that x is technically x to the positive 1, and that 8, or any constant, is that number times x to the 0 power. So x to the 1 would be odd, and this 8x to the 0 would be even. So if the exponents are even, then the function is even, which means it is symmetric across the y-axis, which means it flips across the y-axis. You could fold it on the y-axis, it's going to line up. If all of the exponents are odd, then the function is odd. That means it's going to be symmetric about the origin. You can turn your graph upside down. It's going to look exactly the same. No change whatsoever. Now, if you were to have a mismatch, the function would be neither. There would be no symmetry whatsoever. No symmetry. So we're going to look not even at the graphs. We're just going to look at these functions and determine if they are even, odd, or neither. So we're looking at the exponents. I've got an exponent of 4, an exponent of 2, and remember with the constant, this is x to the 0, so an exponent of 0. So 2, 4, and 0. These are all even. Technically 0 is not even, but that's in a whole nother debate. So these are even. So these are going to be symmetric. We said even is symmetric across the y-axis. So I would say symmetric across y-axis. All right, number 2. I've got x to the 3. I've got x to the 1. So 1 and 3, those are both odd. We said when it was odd, it is symmetric about the origin. All right, number 3. I have an exponent of 3. And then this is technically negative 2x to the 0. So to the 0, well, those don't match because 3 is odd and 0, we're going to consider it even. Once again, it's not really technically even. So in this case, there's not going to be any symmetry. And then looking at our last example, I've got 5x to the 1, I've got x to the 4, x to the 3, and then this last one is x to the 0. So I've got 1, 4, 3, and 0. I've got odds and evens, so once again, this is no symmetry. Now you can always graph these and see if they do end up looking symmetrical, but if you know your rules about your exponents, you don't even have to graph it. You're going to save yourself a lot of time just by being able to look and see, are they all odd, the exponents? Are they all odd? Are they all even? Or is it a mixture? And that will tell you what kind of symmetry you have.